Welcome all to week 9 of the problem solving session for the NPTEL course Dynamical System and Control. So today we will briefly go through the topics covered in the week 9 of the recorded lectures, and then we will solve some problems based on those topics. So let's quickly go through the main outcomes of week 9. So week 9 basically covers the controller design and observer design for linear time invariant systems, and also using Lyapunov function. We also constructed control for a nonlinear system as well. So let's consider the uh, state feedback control design. So in the previous week also we discussed few problems on how to design a state feedback controller for a linear time invariant system of the form AX plus BU. So first thing is that we have to check whether the system is controllable or not. So because if the system is not controllable, then we cannot design U such that all the states of the system can be transferred to some final state. So first we have to check for the controllability of the system. For that we can check for the matrix P, A, B, A square B up to A n minus 1 B. And then if this controllability matrix is of full rank, then we can design a state feedback controller of the form K into X, where K is a row matrix K1, K2 up to Kn, and X is obviously a column vector. So K into X will give us this scalar because U is a scalar function. So here we are considering a single input, single output systems. Then we say that if we design this K such that A plus BK, such that this A plus BK is a stable matrix, that means it has eigenvalues with real part negative, then the system can be transferred from arbitrary initial state to the final state, which in this case is the origin. Alright, now suppose, so this was the case for single input where B is some n cross 1 matrix. Now suppose B matrix is of the order n cross m, of the size n cross m. That means we are considering multi-input system. Okay. So how to design a feedback controller for such systems? Okay. Now procedure remains the same, but the important thing that comes over here is that if our original system, which was x dot equals to ax plus bu, if this is controllable, where where B is some n cross m matrix, then we can convert our original system to the form of x dot equals to bk1 into x plus b1 some function v, where our state matrix converted to A plus BK1, and our control matrix is converted to B1, where this is an n cross 1 vector, and this A plus BK1 is obviously an n cross n matrix, and V is nothing but a scalar function which we can design. So here that u gets converted to some function v that is arbitrary, which we can design as per our choice. So now this when this original system can be converted to this form, then the task gets reduced to designing v of the form k2x, that is the state feedback controller v. Now if this system can be converted to this form, single input form, then how can we design this k1? What would be this k1? So for such systems, k1 is given as some matrix n into m inverse. Now what is this n and m matrices? So there is a procedure to construct n and m. So first we have to check for the controllability, if the system is controllable. For multi-input case I am talking, this m can be constructed of the size n cross n, and this m should be constructed in such a way that its first column should be the first column of matrix B. So suppose our B is of the form B1, B2, Bm, then the first column of M will be B1. Then we will find AB1, and if this AB1 is linearly independent to B1, then we will keep this AB1. Then we will find a square b1, and if this a square b1 is independent to b1 and ab1, then we will keep this a square b1, and we will go till r minus 1 into b1, such that this m should be n cross n. And if in doing so we get some r1 such that this column becomes linearly dependent with this, then we stop over there, and then we will again start with b2, and same we will do with ab2, a square b2 up to a r2 minus 1 b2, and if that gives us linearly dependent vector, then we will move with b3 and so on. And we have to do this until we get an n cross n matrix. All right, so this is how we will design m. Now based on our design of m, n is constructed as m cross n matrix, where its first column will be of the form 0, 1 and all 0, and this 1 will come on the place of r1. So suppose r1 here is 2, then we will write this 0 0 0 0 0, and the second will be this 0 1 0, and then if r2 is 2, then this will be 0 0 0 first, and then second will be 0 0 1, and then 0 0. Okay, so like this we have to design n such that we get an m cross n matrix, and the first one will come on this second entry on the r1th column, and then similarly from r1 to the r2th column, and so on, such that we get an m cross n matrix. So this is how we can design m and n, which allow us to design our k1 such that the system is converted into single input system form, and then we can design our v such as it is k2 into x. Okay, so So that's all about state feedback controller. Now let's move on to observer design. Now similar to our state feedback controller, an observer is designed. So if we have a linear time invariant system and we have the measurement as Cx as the output, so first we have to check for observability by constructing our matrix C and so on. And then if the system is observable, then we can design our observer, which is written as estimated state x hat. So x hat means the estimated state. So x hat is written as the copy of the system. So we'll write the copy of the system, which is a x hat plus bu. Obviously we cannot use x because x is not available to us. What is available to us is y. So in estimator we have to use only those signals which are available to us. Alright, so we write the copy of the system and then the correction term. So we write the correction term as some matrix B into C x hat minus y. Y is available to us through measurement and these x hats are the estimated states. So the x tilde, which is the error, x minus x hat, the error system is given as a plus mc into x tilde. Now we know when this error will converge to 0. This error will converge to 0 only when the state matrix is stable, and the state matrix will be stable only when M is constructed such that this A plus MC has eigenvalues real part negative. Then this x hat will converge to 0, means x minus x hat will converge to 0, obviously as t tends to infinity. So that means x hat will converge to x. So our estimated state will converge to true state x. Now sometimes for the uh, controller design and observer design, it is possible that some states are not observable and some states are not controllable, and that we can analyze through our controllable and observable matrices by converting them into Jordan form. And if that is the case, then it is also possible so now if our system is not controllable means our controllability matrix is not of full rank but of reduced rank. So it is of reduced rank, then that means we can control some reduced states, or we call them manifolds. So it is possible to convert the system into controllable and uncontrollable form as some state by 1. So it is possible to construct Q and P such that the system is converted to controllable and uncontrollable modes. Okay. So now you can see over here that y1 can be controlled using this control input u, but in our y2 there is no control input, so this y2 remains uncontrollable. Now the question is, if the system is converted in this controllable or decomposed into controllable and uncontrollable form, then is it possible to stabilize the system? So from here comes the notion of stabilizability. So stabilizability. Stabilizability. So what it says that if it is possible to stabilize a system, then the system will be stabilizable, and when the system is controllable, then it is always possible to stabilize the system by designing a feedback controller and designing the matrix K such that the eigenvalues lie on the left half plane. But what if the system is not controllable? So suppose the system is of this form, then obviously we cannot design a state feedback controller K such that all the eigenvalues are on the left half, because the system is not at all controllable. Then how can we stabilize the system? So the stabilizability means, so we don't have to uh, worry about the controllable modes, because anyhow we can design a controller U to stabilize the states y1. Now stabilizability says that if the uncontrollable modes are stable, then the system is stabilizable. So that means that through U we can stabilize our state y1, and suppose that this uncontrollable mode, which in our case is y2, if it is stable, and it will be stable when this state matrix q2ap2 has eigenvalues on the left half plane. So if this matrix is stable, then whatever happens to y1, that is in our control, we can design the controller. But this y2 becomes naturally stable through its own dynamics. Alright, it will be naturally stable through its own dynamics, and hence y1 will get stabilized through the controller U, and y2 will get stabilized through its own dynamics. So the whole system will be stabilizable or can be made stable. So that's why we say we have the notion of stabilizability, where we say that if the uncontrollable modes are stable, then the system is stabilizable. Okay, and then we covered the discrete time systems, where we write a discrete time system as x of k plus 1 equals to a of xk plus b of uk, and this k, we call the system as discrete because its argument, we have updates of the system states in discrete time. uh, this k is discrete, so at discrete instance we have the information of the system only at this some instance of time. So this k varies from k naught plus 1, k naught plus 2, up to some infinity, and this you can see that k is incremented by one steps only. So we have k naught plus 1, k naught plus 2, and this k naught belongs to any we can say minus n to n. So it can be -1, -2, -3, or anything, or 1, 2, 3, or 0. whatever we can have based on our system. Now if we have the system in discrete form, then what about its state transition matrix? So state transition matrix should also satisfy the properties that we had for continuous systems. So here also our state transition matrix. So for this system where A is a constant matrix, then in such case our state transition matrix is very simple to design, and this you can derive by induction. So you can just write x of k plus 1, then write x of k plus 2, and wherever we have x of k plus 1 we can put this, and by doing so we can get easily find that you will have something like a of k minus k naught, x of k naught type of thing. So from here our state transition matrix uh, comes out to be a to the power k minus k naught. So here I am talking about when these state and control matrices are constant. So when we have discrete time systems, state transition matrix is given as a to the power k minus k naught, and then it also satisfies all those properties that we had for continuous time system. So phi of k plus 1 is given as a of phi k k naught. So these are very important to remember. Phi of kk is obviously identity. Phi of k naught k is inverse of k naught, k naught, and phi of k naught is some k1, and then k1 to k naught. So obviously k is greater than k1 is greater than k naught, we have to remember. So for constant matrix we have this state transition matrix. Sorry. And now for the case when we have and the solution is written as x of k is phi of k naught, x of k naught, and plus similar way that we had for continuous time system, I equals to k naught to k minus 1 phi of k and I plus 1 b u I. So is the solution. Now suppose we have a time varying system where a is a function of k and b is a function of k, then in that case this solution x of k is given as phi of xk naught and plus I varying from k naught to n, sorry, we can write, so we are writing for k, so it is k minus 1. B will be function of I and then ui. Okay, so this covers the important topics that have been that is there in the recorded lectures. So now let's go through some questions. So let's go through problems based on that. So let's start our first problem. So consider that we have controllable system which is given as x thought is ax plus bu, where A is a matrix 0, 1, 0 and 1, 0, minus 1 and then 2, 1, 1. and B is 0 to 1 and 101, and this controllable system is converted into system of the form y dot is a plus b k1 into y plus b1 into v, where b1 represents the first column of b and k1 is given as n into m inverse. Then we have to find the matrix M. Now it is already given the system is controllable, then this can be converted to this form, but how can we identify what this K1 is? So we have already seen that this K1 is given as a matrix n into M inverse, and M we know how we can find, but the question asks only about n. Now for finding out n, we must know the structure of M. So let's try to find the matrix M for our case. So since it's a 3 cross 3 system, so M will be a square matrix of size 3. So its first column will be B1, that is the first column of B, which is 0 to 1. Okay. Now its second column will be the matrix, the vector AB1. So when we calculate AB1, it will be 2 minus 1 3, and you can see that these two columns are linearly independent, so we are good to go. Now the last remains, because we have to find a square 3 cross 3 matrix, so the third will be a square b1. Now when you calculate a square b1, you will get minus 1 and minus 1 and I think 6. Now when you find its determinant, you will get it to be not equal to 0, so that means this is full rank, and full rank means all these vectors are linearly independent. So this is our matrix M. Now based on this matrix M, we have to construct our matrix N. Now from here we can see that the general form of this is a to the power r1 minus 1 b1. So r1 minus 1 is 2 in our case, so r1 is 3. That means the 0 1 0 0 thing will come on the third column. Third column means, so now what should be the size of n? Since it is 3 cross 2 and it is 3 cross 3, so it must be 2 cross 3. Okay, that is m cross n, and the first column will be 0, second column will be 0, but third column will have the form 0 1. Okay, so this is our r1th column. So this is how we can identify n. So now we have m, we have n, we can convert our system of the form a plus bk1y, and b1 is nothing but the first column of B matrix. So this system can be converted into this form, and then we can design our scalar input B for this uh, system. Similar to this, we have second question. We have our second question. Now, like before, consider that the system is controllable. Consider x dot equals to ax plus bu is controllable, where a is 0 1 1 1 0 0 and 1 0 1. B is given as 1 0 0 0 1 1. Now again this system can be converted to y dot equals to a plus b k 1y plus b1v. We have to find n and m such that this k1 is n into m inverse and b1 is the first column of B. Give this a try. Okay, let's solve this problem. Now for this problem, we can again follow the same steps. First, construct the matrix M and let the size it is of 3 cross 3. And the first column is B1, which is 1 0 0. Second is AB1. So AB1 will be 0 1 1, and these two columns are linearly independent. And then let's check out a square b1, so it is 2 0 1. So obviously all these three columns are linearly independent, so this is the m that we can consider. And then what should be n? So n should be the r1th column will have the form 0 1 0 0 0. So r1th here is again here this r1 minus 1 is 2, so r1 equals to 3. So the third column will be of the form 0 1 0 0 0. And what should be size of n? It should be 2 cross 3 because B is 3 cross 2. So 2 cross 3 means the third column should be 0 1 0 0 0. So it is 0 1, and since we have no any row, so it is just 0 1. Okay. Now suppose that if a square b were linearly dependent to b1 or ab1, then we should go for b2. So we will write here b2, and in that case r1 will be 2. So the second column will have the form 0 1. Okay, so like this we have to construct our matrices M and N. Now let's take the third question. Consider the system So we have this A and B matrices given, and we are interested in designing a controller U of the form Kx. Okay, then we can design this the feedback matrix K if and only if. So this K will exist for controlling the system x dot equals to x plus bu if and only if alpha equals to what? What should be the condition on alpha such that we can design a matrix K in order to control our system x dot equals to x plus bu with A and B given over here. Okay, we know that the feedback matrix K will exist only when the system is controllable. Okay, so let's check whether the system is controllable or not. So for that we have to find out the controllability matrix, and the controllability matrix is nothing but B AB square B, because uh, we have a 3 cross 3 matrix. So B is given as 0 1 alpha, and BAB you can calculate, and then you will get it as minus alpha 1 plus alpha and alpha, and the third column similarly will be of the form, okay, this. And from here we know that the system will be controllable if and only if it is of full rank. That is, for this case it should have rank 3, means its determinant should be not equal to 0. So let's calculate the determinant of our controllability matrix C naught, and so let's check out. So I'm writing the calculation, you can verify. So these will cancel out, so we'll be left with alpha q. Okay, and this determinant will be non-zero only when this alpha is not equal to 0. So the condition for system to be controllable such that we can design a state feedback controller u equals to kx is that this alpha should not equal to 0 is the answer. So now let's take up the question on the observer design. Okay, consider that we have the system a second order system of this form, and now the output is the state state x1. So based on this measured output we have to, so x1 is already available to us, so we have to construct an observer such that this x2 becomes available to us as well. Okay, suppose we have constructed an observer, and then we have this matrix A plus MC whose eigenvalues are minus 1 and minus 3. Okay, so for this system we have constructed an observer such that the matrix A plus MC has eigenvalues of minus 1, minus 3. Find the estimator equations. So now if that is the case, then what would be the equations of the estimator for this system? Okay, just give me a moment, my tab got disconnected. Just give me a few minutes. Sorry for the this actually okay, anyway, let's continue from where we left. Okay, so we are to design the estimator such that this A plus MC matrix has eigenvalues lying on -1 and -3. Okay, so what should be the structure of our estimator? We know that an estimator or an observer is uh, have the form x hat, which is the estimated state estimation of the true state x, is given as the copy of the system ax hat plus bu and plus the correction term, and the correction term we write it as minus m cx minus cx hat, and so the error signal, that is x minus x hat, gets converted to the form a plus mc into x tilde, and for this a plus mc we have our eigenvalues on -1 and -3. So let's consider that our matrix M, uh, obviously it should be of the form uh, column vector. So let's consider that this M is having scalars m1 and m2. And what is A in our case? So for our case this is a linear system, so by seeing the state equations we can write our matrix A is nothing but, so the first one we can see that we have no x1, so it is 0. For x2 we have coefficient 1, and similarly over here coefficient of x1 is -1, coefficient of x2 is -1. This is our A matrix. And B, there is no control in the first stage, so it is 0. There is control in the second with coefficient of 1. So these are our A and B. And C is obviously only the state x1, so it is 1, 0. Okay, so these are our A, B and C matrix. Now let's find out this A plus MC thing. So A plus MC can be written as A plus MC can be written as, it is 0, 1, -1, -1, and plus m1, m2, and C is 1, 0. So when we calculate it, this would give us m1, m2 -1, 1, -1. Okay, now its eigenvalues are lying on -1 and -3. So when we write the characteristic equation, so the characteristic equation, that is lambda I minus A plus MC determinant, when we calculate, it would give us lambda minus m1 minus 1, lambda minus m2 minus 1, and then minus m2 minus 1, and then lambda plus 1. Okay, so that means we have the characteristic equation lambda minus m1, lambda plus 1, and minus m2 minus 1 equals to 0. So we have lambda square, and then lambda terms we can combine So that will be plus lambda minus m1 and plus 1, and then the constant terms are minus m1, so it is minus m1 plus m2 minus 1 equals to 0. And it is given that its eigenvalues are on minus 1 and minus 3. So this is basically equals to lambda plus 1 and lambda plus 3, which is equal to lambda square plus 3 and plus 1, 4 lambda plus 3. So that means this coefficient matches this, so minus m1 plus 1 should be equal to 4. So m1 should be equal to minus 3, and this minus m1 plus m2 minus 1 should be equal to 3. So now m1 is already minus 3, so it is minus 3 minus 1 minus 4, and 4 plus m2 equals to 3, so m2 equals to 1. So now we can write our estimator. Our estimator is this. That means we have the estimator of the form x1 dot equals to A matrix is 0, 1, minus 1, minus 1, and B matrix is 0, 1, U, and minus M. So M is M1, M2, so M1 is minus 3, sorry, M2 is minus 1, minus 3 and minus 1, so it is 3, 1 into C, and then or we can write Cx as x1 minus x1 hat, obviously. So we can write each equation as x2 hat plus 3 x1 minus x1 hat, and x2 hat equals to minus x1 hat minus x2 hat plus u and plus x1 minus x1 hat. So this is the equation for our estimator or observer. So uh, when we simulate this in MATLAB with this as our true system and only using the state x1 as our measurement, and when we propagate this dynamics using this x1 only, u can be anything, so we will observe that this x1 hat will converge to x1, the true one, and x2 hat will also converge to x2, or obviously asymptotically, so as t goes to infinity. Okay, so I will show you how to simulate this type of observer in MATLAB, and then you can also see how these states converge to estimated one converge to the true one. But before that, let's look on our last question. Okay, so for a given system, x1 dot equals to x2 and x2 dot as minus x1 minus x2 plus u. Find the controller u such that x1 and x2 tracks the desired signal x1, where x1 desired is half and x2 desired is 0. So for using Lyapunov. So we are given a linear system. Obviously we can check that is a linear time invariant system. So for this system we have to design our controller U, which can be anything. So that could be a constant value or a state dependent value, anything. So we have to design our controller U such that the states x1 and x2 tracks the desired signal. So x1 should track the value of half, that means x1 should settle to value 0.5 and x2 should converge to 0 asymptotically. And this we have to do using the Lyapunov theorem. So now let's see how we can design such controller U. So let's recall what does Lyapunov say. So it says that for positive definite function V, so positive definite function V x1 x2 means it is greater than 0 for x1 x2 not equal to 0, and it is 0 only when x1 x2 are 0. So for a positive definite function V, if we can construct the derivative of V is negative definite or semi-definite, then our system, then our states, or then V will converge to, or you can say that so we are considering for a system and U is some function of x. Then if V dot is negative definite or semi-definite, the system will be asymptotically stable for negative definite case or only stable for semi-definite case. Okay. So the first task for this problem is to choose a Lyapunov function. So a very common approach is to use a quadratic function. So let's okay. Now since it's a tracking problem and it's not a stabilization problem, so tracking problem involves stabilization of the error dynamics. So let's derive the error dynamics for tracking these desired signals. So let's write the error error E1 as x1 minus x1 desired, and x1 desired is just half, and x2 is the x2 minus x2 desired. So x2 desired is 0, so E2 is nothing but x2. Now we have to uh, find the controller such that this E1 and E2 converges to 0 as time goes to infinity, because when E1 and E2 converges to 0, our x1 will converge to x1 desired and x2 will converge to x2 desired. So for this system, let's find out the dynamics then. Now E1 dot is nothing but x1 desired minus x1 desired derivative, and x1 desired derivative is nothing but x2, and x1 desired derivative is 0 because the derivative of constant value is 0, so it is nothing but 0, and x2 in terms of E1 and E2 is nothing but E2, so E1 dot is E2. So this is our first dynamics, and similarly we have to write for E2 dot. E2 dot is nothing but x2 dot, and x2 dot from our system dynamics is minus x1 minus x2 plus u, and minus x1 for our case, we can write x1 in terms of sorry, x1 we can write in terms of e1 as minus so x1 minus x1 is e1 minus x1 desired, and then minus x2 and x2 is nothing but the signal e2, so it is minus e2 plus u. So this is our error dynamics for e2. All right. Now let's construct the Lyapunov function b as half of e1 square plus half of e2 square. And then, so this is a positive definite function because e1 square and e2 square are always positive, except at the origin it will be 0 at the origin only. So it's a positive definite function. Now let's calculate its derivative. So its derivative, when we calculate, so first we have to find derivative with respect to e1, and then using the chain rule we have to find the derivative of e1 with respect to time. So that would give us e1 dot, and for the second also we get e2 dot. Then now let's uh, uh, put the dynamics equation. So it is e1 and e1 dot, we have e2, and e2 dot we have e1 minus x1 desired minus e2 plus u. Also there's mistake over here. So when we find minus x1, so minus x1 you can see that um, I have to tell. So minus x1 will be minus e1, so here it will be minus. Yes, so now it is minus. Now it will give us minus e1 e2 minus e2 x1 desired minus e2 square, and then plus u e2. So here these terms cancel out, and this is a negative term, so that is good to us. And then we have some sign indefinite term, which is e2 and u minus x1 desired. Now the objective is to make this Lyapunov derivative negative definite, such that our v will be decreasing and converging to 0, and when v converges to 0, that is only possible when both e1 and e2 converges to 0, because we have constructed v as a positive definite function of e1 and e2. So let's choose our controller u such that it cancels this term x1d, and then let's consider any gain k which is greater than 0 into e2. So when we choose this type of controller where k is anything greater than 0, then what we will observe that we have v dot equals to minus e2 square and minus k e2 square, so it will give us nothing but minus 1 plus k into e2. Okay, e2 square. Or we can choose any k greater than equal to 0. Okay, so when we have this, we get v dot as e2. Now v dot should also be negative definite, means it should be negative for all values of e1 and e2, and it should be 0 only at the origin. So but from here what we see is that v dot is a function of e2 only. So when e2 is 0, v dot is 0. But what about e1? E1 can be of any form. But you can observe from here that when e2 is 0 and you see the dynamics, so when you see the dynamics, so let me write the dynamics. So we had e1 dot as e2 and e2 dot as minus e1 minus x1d minus e2 and plus u. So u is our x1d minus k e2. So it is minus e1 minus e2 minus k e2. That means it is minus e1 minus 1 plus k into e2. So this is our e2 dot. Now when we put e2 equals to 0, put e2 equals to 0 means e2 dot is also 0. So e1 dot will be 0. And what about e2 dot? E2 dot, since it is 0, then this right hand side should also be 0, means minus e1 minus 1 plus k e2 should also be 0. Now e2 equals to 0, this term will go to 0. The only possibility is that e1 should be 0. Okay, so when e2 is 0, the only possibility is that e1 is also 0. Now that means that v dot is negative for all values of e1 and e2, and it is 0 only when e2 is 0, and that implies e1 is 0. So our v dot is negative definite. So when our e dot is negative definite, which means that v will converge to 0 as t goes to infinity. That means our system comprising of the states e1 and e2 are asymptotically stable, means e1 will converge to 0 and e2 will converge to 0. That means x1 will track the desired signal x1d, that is the value half, and x2 will track the desired signal x2d, that is the value 0. Okay, so this is how we can design a controller based on the Lyapunov analysis. Okay, so in the next week, I will show you MATLAB simulations for both of these examples where we have constructed an observer, the previous question, and this controller question. So I will show you how we can simulate these observers and controllers, uh, specifically using Simulink, because MATLAB code you can just use any AI, but when it comes to Simulink, it needs a visualization. So purposely I will show you how we can implement these observers and controllers using in Simulink, and then we will see whether these theories are actually working or not. So if these theories work, or if these constructions are true, then we will see that the estimated states converge to the true ones, or uh, our states are tracking the desired signals, and so on. Okay, so that's all for today. So we will meet next week to have some more problems, and also some work on simulations. So thank you.